Our next example will be to show that the function f of x equals 1 over x is uniformly continuous on this particular domain from 1 to infinity. Now before we do that proof, let's recall what the graph of f of x equals 1 over x looks like. Something like this. Now the reason I'm showing the graph is that it should be fairly clear that if I took the interval from 0 to some number, 0 to infinity, it doesn't have to be that to 0 infinity, let's say it goes 0 to 3. On this interval, this open interval, f of x equals 1 over x is not uniformly continuous. It's similar to the reason that the graph that f of x equals x squared was not uniformly continuous over its domain. The reason is that as you get close to 0, from the right side here, the function is blowing up towards positive infinity. That's what prevents it from being uniformly continuous from 0 to any number out this direction. It's not uniformly continuous from 0 to 1. But starting from 1 to infinity, it is uniformly continuous. And that's what we'll prove. All right, once again, since uniform continuity is a little bit new, we're going to do the definition. It's uniformly continuous if, for every epsilon greater than 0, there exists a delta greater than 0 such that if x and y are two values in the domain, which our domain is 1 to infinity, and x and y are very close together within delta of each other, that implies that f of x minus f of y in absolute values, that distance is less than epsilon. All right, that's the definition. So to show this, we're going to just start off by saying let epsilon greater than 0 be given. This is just an arbitrary value, positive number, epsilon. It can be anything we want that's positive. Now, there exists means we have to find the value of delta. And I don't know what value to choose yet. I'm going to proceed with the proof and come back and fill this in when we get near the end. Okay, so choose delta to be some value. Thus, x minus y less than delta implies, and let's see what that implies. If this is true, I have to show that this is true. So I need to say f of x minus f of y, and eventually I'm going to get less than epsilon. So what is this equal to? Well, it's 1 over x. So f of x is 1 over x minus 1 over y, f of y. Maybe I'll go a little farther to the right. Now I think I'm going to combine those into a single fraction with the common denominator being xy. I would get y minus x over xy. Now, what can I do? Well, to simplify this, can't I just say this? I think I can. Why is that the case? Because x and y are both numbers from 1 to infinity. So I'll say that x and y well, let's just say that they're greater than or equal to 1, if they're in the domain here. Greater than or equal to 1 implies xy is greater than or equal to 1. That's the justification for removing this. We're getting a bigger number by removing this denominator. And I don't need to do it, but I'll reverse those. x minus y. So, what do we know about absolute value of x minus y? It's less than delta. What I need it to be is less than epsilon. So guess what I'm going to choose to be epsilon? Delta. And that's the end of the proof that 1 over x is uniformly continuous on this interval from 1 to infinity.